Steinhauer here, welcome back. We have taken a star to the main sequence and now off of the main sequence, and we have gotten it to be fusing helium in the core. The question now is, what happens after it runs out of helium in the core? Because it will eventually run out of helium in the core. Well, it's very similar to running out of hydrogen. You run out of that heat source and energy source in the middle, and that makes you start to have a carbon ash core that isn't fusing anything. That will slowly contract in on itself. The layers above it, you'll start helium fusion will still be occurring in a shell around that carbon ash core, and it will contract down and get hotter, and all of the fusion reactions will get stronger and faster. The hydrogen burning shell is still going on around that. That will contract and get hotter as well, and you'll be able to fuse helium in regions you weren't able to before. You'll be able to fuse hydrogen in regions where you weren't able to before. All of this leads to actually, again, despite running out of an element to burn in the core, an increase in the total amount of energy that's generated as the core shrinks and contracts and heats up. And so that increase in luminosity pushes the outer parts of the star outwards. The radius expands, luminosity goes up, the temperature drops again, and it moves back up and to the right on the HR diagram. This is what the interior of that star might look like in cartoon form now. Again, not to scale. This isn't even visible on this scale, where this is the outer part of the star down here in the center, but you've got now a carbon core that isn't burning anything, with maybe a little oxygen thrown in there too. You're burning helium in a shell around that, and you're burning hydrogen in a shell around that. And it will become a supergiant. It will be even larger than it was before. Now it's, for a star like the sun, almost out to Earth's orbit in the solar system, and we'll be in big trouble. We'll be in trouble in the first time the red giant branch happens, but we need to be long gone by then. Okay, so what's the general pattern? It is that you burn an element in the core, first hydrogen and then helium. You run out of that element in the core contracts, you burn that element in a shell, and until the core gets hot enough to burn the next element, in which case the next element starts burning. So this is the end for low mass stars like the sun. The sun and low mass stars less than 2 solar masses or so, will never get hot enough for carbon burning to take place. And so that the sun ends with a carbon oxygen core, the helium shell gets hotter and denser. And so you get this series of things happening where the core contracts and heats, helium burning begins, and you get sort of a shell flash of helium, and that makes the entire outer part of the star and inner part of the star expand. It cools off, and you don't get any fusion anymore, and then it slowly contracts in on itself until you get another helium flash. And these helium flashes can occur over and over again, and these helium flashes can impart a large amount of energy to the outer part of the star, and in fact push the entire outer part of the star basically out into space. They lose gravitational connection with the entire core of the star, and eventually the entire outer part of the outer envelope of the star is lost to space. It is ejected. It is slowly pushed away by these helium shell flashes into space. And you've still got the very hot, dense core of what was the star before, and it will heat up that nebula and make it glow rather nicely for hundreds of years in some cases. Here's we call these things planetary nebulas, which is a terrible thing to call them because they have nothing to do with planets. But when you look at these things through telescopes, and here's an example of one, they kind of look like planets. Why do they look like planets? Well, planets, you can tell from stars through a telescope because you can see the radius. They have a disk to them. They look like disks in the sky. Well, these things also kind of look like disks in the sky. And so through a telescope, some of them kind of look like planets. So that's where they get the name planetary nebula, but they have nothing to do with planets whatsoever. And you can see, this is a classic example of a planetary nebula. the outer part of this star has been pushed away into space, and look what's here at the center, the hot, very hot, dense, exposed core of that star, probably just carbon and oxygen. These things come in an amazing array, though, of shapes and morphologies, depending on how those helium shell flashes actually happened and how violent they were. Here are an example of a couple more of them. This is the Helix Nebula, I think, but in each one of these, you've got in the very center an exposed core of that star, and you're seeing the outer envelope of the star pushed into space and still glowing because it's being heated by that very hot, dense object at the center. So what is left behind? What is that object at the center? It is the core of this that's been exposed of that dead star. It is still extremely hot. At the beginning, it has a temperature of more than 100,000 Kelvin, even at the surface of it, and it's extremely small, a radius something typical, something similar to the radius of the Earth. This circle with a plus sign in it is the symbol for the Earth. And it's extremely dense. Densities on the order of 10 to the 9 kilograms per cubic meter. What do we call such a thing? Well, we've seen these things on the HR diagram, and we were wondering what they were. These very small, hot, dense things, we call them white dwarfs. We'll talk more about these white dwarfs in a minute, but let's first, would you like to see some more pretty pictures of planetary nebula? Of course you'd like to see some more pretty pictures of planetary nebula. So here we go. Some more pretty pictures of planetary nebula. Again, there is no limit. It's kind of like a fingerprint. They all look different and they all look spectacular in their own ways. And they're all sort of color enhanced in this particular case to bring out and highlight some contrasts in these images, but still spectacular no matter how you look at it. Here's a few more. We've got the Dumbbell Nebula in the upper left. We've got I think this is the Eskimo Nebula in the lower left. This one's called the Ghost Nebula. These all have interesting names because they're fascinating and some of the most photogenic things in our galaxy to look at with a telescope. Here's some more. They're not even all round. Here are some that have peculiar shapes. You can see, depending on how that material is ejected, sometimes it's ejected spherically, but sometimes the material that's ejected seems to be nozzled in a couple of different directions, either by strong rotation or magnetic field or something like that. You can almost see in this one in the lower right, where this kind of looks like a garden hose on fairly low stream. You can just see the nozzling effect as the material that's being ejected from the star gets nozzled in both directions at once. And this is sort of a similar thing. You've got a couple of lobes here and clearly an asymmetric two-lobed ejection of the material that's coming out of this particular star. This one looks weird. You've got this sort of boxy square-like thing, but probably you're seeing something like this only directly from the side. So you're seeing the nozzling happen in this direction, but you're seeing it from the side, and so it looks like this boxy thing. Here's one where the streams of this are energetic enough that the material is being ejected way out into space and continuing in these long plumes. But these are all the same effect. You've got a star, a low mass star at the end of its life, slowly sloughing off its envelope into space and having it glow for several hundred years afterwards. Okay, so here it is, the definitive complete life track of a star like the sun, a low mass star like the sun, after the main sequence. Star starts on the main sequence, and as soon as it runs out of hydrogen in its core, it moves up the giant branch, first the subgiant and then the red giant branch. And while it's doing that, it is in this state right here, where it is not burning, it has an inert helium core, and it's burning hydrogen in a shell around that. As this inert helium core gets more and more massive and hotter, it eventually reaches the tip of the red giant branch where the helium flash will occur, and then it will immediately move down here to the horizontal branch, and here is the helium burning main sequence. You'll have a helium burning going on in the core, and you'll have hydrogen burning going on in the shell around that. Eventually, you'll run out of helium in the core, and you will move up, back up and to the right again on the HR diagram, and that will be this diagram. You've got an inert carbon core now. You've got helium burning going in a shell around that, and you've got hydrogen burning going on in a shell around that. And again, this gets hotter and hotter and hotter. These helium shell flashes happen, and then the outer parts of the star are lost altogether. And then, depending on whether you're talking about the planetary nebula, which will still be fairly bright, or the white dwarf, which will be fairly dim, but extremely hot, you sort of, as soon as that white dwarf is exposed, it lands down here on the white dwarf track. And these guys will just cool off over time very slowly because there's nothing left now. There's no fusion happening. These are the dead remnants of stars, these white dwarfs down here. Okay, so these white dwarfs are really interesting objects in their own right. Here is a picture of the brightest star in the sky, Sirius, in the visible light. And if you look closely, you can actually see a secondary object right down there. That's actually a binary orbit with Sirius A. So this is Sirius B. Sirius A is the brighter one, obviously, and these two objects are orbiting one another, right? If you look at the same thing in the X-rays, this is Sirius B and this is Sirius A. This object that was so faint in the visible is actually brighter in the X-ray than Sirius, than the brighter star in the visible. So Sirius A is the dim one here, and Sirius B is the brighter one in X-rays. Remember, X-rays are really high energy photons, and so if you have a very, very hot object, it will be emitting more X-rays, more high energy photons, than it will be low energy photons. And so even though this object is so faint in the visible part of the spectrum, it's actually brighter than Sirius in the X-ray part of the spectrum. And this is a white dwarf. This is the nearest white dwarf to us, a binary companion to Sirius, the brightest star in the sky. So Sirius B is one of these white dwarf stars. Okay, here's a final question for you. As we exit this post-main sequence evolution of low mass star segment, and that is, how much would 1 cubic centimeter of white dwarf material weigh on the Earth? Now, this is an extremely dense material. What is 1 cubic centimeter, though? Cubic centimeter is about the size of a dice in your Yahtzee set. So that's about a cubic centimeter on a side. So, or a teaspoon, right? So a teaspoon would be about a cubic centimeter also. So how much would that weigh? If you could scoop up a teaspoon of white dwarf material and bring it back to Earth, how much mass is that? Now, you couldn't do this for many reasons, but if you could, how much mass would be there? Well, we need an equation to be able to understand this. And you might see this Greek letter rho here. This is rho, the lowercase rho. Kind of looks like a P, but I'll draw it more curly Q-y than the P's. So this is density. And so if you know the density formula, density is defined to be, the density of an object is an object's mass divided by its volume. Okay, so in this case, we know what the density is. That's 10 to the 9 kilograms per cubic meter. And we know what the volume is. That is 1 cubic centimeter. So we need to solve this equation for the mass and do some fancy unit conversions if we want to be able to solve this equation. So let's solve this for mass first. We can multiply both sides by V. The V's cancel out over here. And if we switch this equation around, we get mass equals density times volume. Okay, so this is 10 to the 9 kilograms per cubic meter times 1 cubic centimeter. Now, we need the cubic centimeter to cancel out with the cubic meter, but that won't work because they're not the same unit. So we need to know how many cubic centimeters there are in a cubic meter, right? And so we need to convert this cubic centimeters to cubic meters. We know that 1 meter is 100 centimeters. So we need to cube these. A cubic centimeter, if we cube both of these, 1 cubic meter, 1 cubed is 1, is 100 cubed cubic centimeters. And 100 cubed is 10 to the 2, 3 is 100 times 100 times 100, and that is 10 to the 6, or 1,000,000 cubic centimeters. So one of those plane, it would take 1,000,000 of those plane dice to fill up a full cubic meter of volume. And so we can use this. We need meters cubed, 1 meter cubed divided by 10 to the 6 centimeters cubed. Things cancel out now. We've got a meters cubed on top and a meters cubed on bottom. We've got a centimeters cubed on top and a centimeters cubed on the bottom. So this is 10 to the 9 times 1 divided by 10 to the 6. And that's pretty easy. You can plug it in your calculator if you want to, but 10 to the 9 divided by 10 to the 6, all you have to do is divide the bases, which are both 1, and subtract the exponents. So this is 1 times 10 to the 3, or just 10 to the 3. And what are the units? They're all gone except for kilograms. All right, so what does that tell us? This is 1,000 kilograms, which is a metric ton. 1 teaspoonful of white dwarf material has the mass of a metric ton. So no, you wouldn't be able to land on a white dwarf because the surface gravity would be too much and you would be squished and it would be too hot and you would be burned up. And even if you could do all those things, you would not be able to lift the teaspoonful of white dwarf material because it would weigh a full metric ton. Okay, so that ends basically the fate of the sun. We know now how the sun formed. We know what will happen to it after it runs out of hydrogen. That is the ultimate fate of the sun, to be one of these white dwarfs. And it will simply cool. There is no life cycle left after white dwarf. There's no helium, there's no fusion happening anymore of any kind. It simply will get cooler and cooler and cooler over time. And this whole thing is still in this electron degenerate state, so it has kind of the same constant temperature and density inside of it as well, which is an interesting fact about white dwarfs themselves. So as this thing cools over billions and billions of years, though, basically it's made of carbon, and eventually it gets cool enough that crystalline structures will form, and the entire thing will kind of become a crystallized carbon thing. What is a crystallized carbon thing? It's basically a diamond, right? A crystallized carbon cool thing is turned, this thing is going to turn into a giant diamond, which has almost the mass of the sun, comprised and almost the size of the Earth. So if you're looking for a way to make a lot of money real quick, you can just head off to the nearest white dwarf. You don't even need much of it. And just break off some of that stuff, bring it back, and you'll have more diamonds than you could ever deal with. All right, all I ask for is 10% of the royalties. Okay, that ends our discussion of the sun. We'll come back in the next class and talk about how high mass stars are similar in their evolution in some ways, and also quite different in some other ways. Great, see you then.